So in this chapter, we learn the sources of magnetic field, sources of magnetism, so in other words, in chapter 27, we focused on when you already have a magnetic field, how does that magnetic field affect another wire, right? And how does it affect loops? But now we want to learn, where does magnetism come from? What creates magnetism? So in other words, what creates B field? And the easy answer is a moving charge. A moving charge creates magnetic field. So it's kind of like the reverse of the previous chapter. In the previous chapter, we said, in order for a charge to experience a force from a magnetic field that is already being created. So imagine in the previous chapter, we didn't worry where this was coming from. We didn't worry about where the B was coming from. So this is a B that already exists. B that already exists. So what we worried more about was, once we know that the B exists, how does that B affect the charge? And we learned that the only way that that B can affect the charge, if the charge is moving, right? The charge has to be moving, and it has to be moving in such a way that it's not in the same direction as the B. It has to be moving like some kind of V that has an angle with respect to the B. Then that magnetic field will exert a force on that charge. Well, now we're learning that to create this B, you need a charge that's moving to create that B, right? So the simplest thing is, of course, a current carrying wire is an example of a charge that's moving. A current carrying wire. So you got a bunch of charges that are moving, right? So the equation for the magnetic field created by the piece of that wire is called Biot Savart Law, probably named after two people, Biot Savart. It's kind of nice to see a little bit of the history too. In physics, specifically electromagnetism, the Biot Savart law is an equation describing the magnetic field generated by a constant electric field. Electric current, I mean. It relates the magnetic field to the magnitude, direction, length, and proximity of the electric current. The Biot Savart law is fundamental to magnetostatics, playing a role similar to that of Coulomb's law in electrostatics. When magnetostatics does not apply, the Biot Savart law should be replaced by Jefimenko's equations. Space. The law is valid in the magnetostatic approximation and consistent with both Ampere's circuital law and Gauss's law for magnetism. It is named after Jean-Baptiste Biot, was a French physics astronomer and mathematician who discovered the Biot Savart law of magnetostatics, established the reality of meteorites, made an early balloon flight, and studied the polarization of light. And Félix Savart was a physicist, mathematician who is primarily known for the Biot Savart law of electromagnetism, which he discovered together with his colleague. His main interest was in acoustics and the study of vibrating bodies, a particular interest in the violin. So that this goes back to 1820 then. Okay, so how does the law go? Yep, this is it. B is mu 0 over I dl crossed into r hat over r squared. I usually write it this way, with the r hat over the r squared. Okay, so let's write it all like this. dB is equal to mu 0 I over 4 pi. So dl crossed into r hat over r squared. So that, in other words, the magnetic field created by this piece at that location, let's say, right, is going to be the dl vector, which is to the right. If the current is flowing to the right, then the dl vector is flowing to the right. The r hat vector is a vector pointing in the direction of that point, you see. And then the r squared is the distance between them. And then the cross product gives you the direction that of that magnetic field, right? So the direction of the magnetic field, dl crossed into r hat, out of the board. So that little piece of wire is going to create a magnetic field here that is out of the board. And we'll call that dB. And then in order to find the total B field of the whole wire, we could integrate over that whole wire, right, from wherever the initial length to the final length. So this is going to be similar to what we did for rods, let's say, where we had a rod and we said, okay, what is the electrical field, let's say, in the center? We took the charge and we said, oh, okay, the electrical field created by a charge is K dq over r squared r hat, right? Where dq is the charge of this, r squared is the distance, and r hat is the unit vector in the direction of that, right? So in other words, the electric field is this way. It's in the same direction as the unit vector pointing to that point, you see. But with magnetism, the direction of the magnetic field is different. You take the cross product of dl into r hat and you get out of the board. So the magnetic field created at that location is not this way. It's out of the board like that. You see. So that's why it's saying dl crossed into r hat instead of r hat. You see. So then mu 0 is going to kind of replace E0, the electrical permittivity. And then there's the three-dimensional version of this, triple integral. Don't worry about that. We don't have to do that. Let's see, where is the constant mu 0? They're not giving it to us here, but we could look it up. Magnetic permeability. So that mu 0 number is called magnetic permeability. And that is this number. Or it's just easier to remember it as 4 pi times 10 to the minus 7. Yeah, that's the easiest way to remember. Magnetic permeability. So it kind of takes the place of the E0, which is electrical permittivity. Okay, so mu 0 is going to be 4 pi times 10 to the minus 7. And what are the units of it? Henries over meters. For now, don't worry about that. This is Newton over area squared. Let's just use that because we haven't even defined what the Henry is yet. So just do Newton per, and then this is area, I guess. Yeah, Newton per square. Oh, no, that's ampere. Newton per ampere squared. Newton per amp squared. Okay, so that's the value of the mu zero. Magnetic permeability. Permeability. So I guess you can kind of word it this way. It's a measure of how well magnetism permeates into a vacuum. Magnetic permeability of vacuum. How well magnetism permeates itself into vacuum space, right? Whereas E0 is 8.854 times 10 to the minus 12. That's called electrical permittivity. Permittivity of vacuum. And we can kind of word that as how well vacuum space allows electricity to flow through it, or electrical fields. So one is the word permit, and the other one is permeate, right? So how well vacuum permits electrical fields to flow through it, and how well vacuum enables magnetism to permeate through it, right? Then when you multiply these two numbers, and then square root it and reciprocate it, what do you get? You probably should know that, Daniel, right?
It's one of those fun little, I guess, I don't know if you can call them an Easter egg, just how interesting the number is.
Yeah.
I don't want to spoil it. I know.
Oh, you don't want to spoil it, right? So it's interesting that when we discovered this, of course, it's probably Maxwell that discovered that, right? So when you do the magnetic permeability and the permittivity, right? And then you go 4 times pi times 10 to the power 7 negative. Okay, so you got a really small number here, this very, very small number for mu zero. And of course, this is even smaller, times 8.854 times 10 to the power 12 negative. Okay, so you get this hugely small number, but then I'm saying square root it. Okay, and now reciprocate it. You got the speed of light, right? 299,795. No, 299,795,637.7 meters per second. Let's see, is that the speed of light? I don't even think we should even call it speed of light anymore. We should call it speed of electromagnetic waves, right? Because light is only one little sliver of the electromagnetic spectrum. All electromagnetic waves travel at this speed. Speed of light. Oh, how close are we? 299, 792, 458. Okay, not exactly the same, we got what, 299, 795. But I probably use the rounded version of the E0. This is not very round, this is not rounded at all. So it's perfect, but the E0, the actual E0 has more digits here. So if I were to use the actual E0, I would do maybe more numbers here, and this would have been smaller. Yep. So it should work out that it gives you the speed of light, which we usually just say 3 times 10 to the 8 meters per second, right? Just for short. 3, 6, 8, yeah. Okay, so now using this, we can then calculate the magnetic field created by straight wires, bent wires, semicircular wires. So here we go again, just like we did for electric fields. We're gonna use the Biot Savart Law. Let's do the straight wire first.